Welcome to Coronachem Day 35 class. This is for grade 12, U and AP. I'm continuing the Kinetics chapter. We have a problem here where they ask us to analyze some data and write the rate law for the reaction. So the question asks, the iodide ion reacts with hypochlorite ion, the active ingredient in chlorine bleaches, in the following way. Hypochlorite plus iodide gives you hypoiodite plus chloride. This rapid reaction gives the following data. A, write the rate law for the reaction. Okay, so the way to approach this is to look at the different experiments, and there's 3 experiments in this question. If you want to find out the effect of the hypochlorite, look for experiments where the concentration of the other reactant remains unchanged. So in experiments 1 and 2, the iodide ion concentration remains 1.5 times 10 to the minus 3. So any change in rate has nothing to do with the iodide. It'll have to be attributable to the change in hypochlorite. And we see that the hypochlorite concentration is doubled from experiment 1 to experiment 2. And we also see that the rate doubles. It goes from 1.36 to 2.72 times 10 to the minus 4. So we see that doubling the concentration of this particular reagent causes a doubling in the rate. That means it's first order with respect to hypochlorite. Okay, then let's look at the other experiment where you could attribute the rate change to the iodide ion concentration. So in trials 1 and 3, the hypochlorite concentration is the same. So no rate change can be attributed to the change in concentration of hypochlorite. Between those 2 same experiments, however, the rate doubles. It goes from 1.36 to 2.72 times 10 to the minus 4. And so does the iodide ion concentration. So they doubled the iodide concentration from 1 to 3, and it caused a doubling of the rate. So because of that observation, we can say that it is first order with respect to iodide. Okay, so we can say the following then. The rate of the reaction is equal to some rate constant K times the concentration of hypochlorite to the power of 1 times the concentration of iodide ion to the power of 1. That is the rate law, according to the data we have here. In part B, it asks, calculate the rate constant. To calculate the rate constant, you need to take one of the data sets and plug it into the rate law. So I said 1.36 times 10 to the minus 4 is equal to the value of K times the concentration. I guess I chose the first data set, but you can choose any one of the 3. Times concentration of 1.5 times 10 to the minus 3 for hypochlorite, and 1.5 times 10 to the minus 3 for the iodide. The value of K then is obtained by taking this number, putting it on there, and then transposing that. No, better way of doing it is to transpose these 2 and put it under here, right? So what we get is K equals 1.36 times 10 to the minus 4 molarity per second over 1.5 times 10 to the minus 3 molarity squared, because it's these 2. And what you get is 60.4 recurring. And the units are molarities to the minus 1, seconds to the minus 1. And because we're only allowed 2 sig figs, you'd have to report it without the 0.4. So you would get 60 as your answer for the value of K. In question C, it asks,
calculate the rate when the hypochlorite concentration is 2.0 times 10 to the minus 3, and iodide is equal to 5.0 times 10 to the minus 4.
Alright, so let's erase this to make room. hypochlorite concentration is 2.0 times 10 to the minus 3, and the iodide concentration is equal to 5.0 times 10 to the minus 4 molar. Then, using the rate equation, the rate law, rate is equal to K times hypochlorite concentration times iodide concentration, and it equals 60.4 recurring times 2.0 times 10 to the minus 3 molar times 5.0 times 10 to the minus 4 molar. The rate will be predicted to be 6.04 recurring times 10 to the minus 5 molarity per second. How do we get that? Molarity minus 1 cancels with molarity. Yeah, so you get molarities to the second, molarities per second, or molarities times second to the minus 1. And you're also allowed 2 sig figs, so you're going to write 6.0 times 10 to the minus 5 as the final answer. Similar question is 1428. So your homework will be, I'll add you the homework questions and that parallel. So this will be your parallel homework question for that question. The next one I want to do with you, oh, I left my, excuse me, 1429 is the next one. The following data were measured for the reaction of boron trifluoride plus ammonia to give a compound where the two are added together. There were 5 experiments done, and it asks what is the rate law for the reaction. I guess I'll just copy the data so you can see how I rationalize it all. There's 5 trials. Concentration of boron trifluoride, concentration of ammonia, concentrate, and initial rate. The reason they measure initial rates is because, as you know, as the reaction proceeds, the concentration of the reagents decreases, and so the reaction diminishes. So at the very beginning of the reaction, it gives you the peak rates at those particular concentrations, or a reasonably good approximation of what they are. So initial rates are sufficiently accurate. So 0.25, 0.200, 5, 0.200, 0.35, 0.175. Ammonia is 0.25, 0.125, 0.100, 0.100, and 0.100. And the rates are 0.2130, 0.1065, 0.0682, 0.1193, and 0.0596. What does it ask?
In the first question,
And the reaction looks like this. I forgot to do that for you. The reaction looks like this. You have boron trifluoride gas reacting with ammonia gas to give you F3B NH3, also a gas. Question. what is the rate law for the reaction, part A? B, what is the overall order of the reaction? C, what is the value of the rate constant for the reaction? D, what is the rate when the concentration of boron trifluoride is 0.1 molar and ammonia is 0.5 molar? How do we rationalize the order of the reaction? Well, I see right away that between trial 1 and 2, the concentration of boron trifluoride is kept constant. So we can attribute any rate change to ammonia, and we see that the ammonia concentration has been halved from trial 1 to trial 2, and so has the rate constant. So twice of this is 0.213. So if you double this, you get that number. So that tells you that it's first order with respect to ammonia. In how did I say it in here? Between experiment 4 and 5, the ammonia concentration is kept constant at 0.1 molar, but the boron trifluoride is doubled from 0.175 to 0.35. The effect on the rate is to make it become 2.0016 times faster, which is an effective doubling with an acceptable experimental error. This reaction 2 is first order with respect to BF3. So these two reactions allow you to determine that it's first order with respect to ammonia, and these two reactions allow you to determine, no, sorry, these two 4 and 5 allow you to determine that it's first order with respect to boron trifluoride, and these two reactions 1 and 2 allow you to also determine that it's first order with respect to ammonia. Okay, so these two are instrumental. So first order with respect to ammonia, and 1 and 2 is first order, shows that it's first order with respect to it's first order with respect to boron trifluoride. This one is first order with respect to ammonia. Am I losing my mind, folks? 1 and 2, BF3 is constant, and it's ammonia, right? Okay. And then for 4 and 5, ammonia is kept constant, but they halve the BF3, and it's causing a halving of the rate. So what is the rate law that you can get from it? The rate is equal to BF3 times NH3 concentration, okay? So it's first order with respect to both of those two reagents. The overall order is 2, which answers question B. Overall, the order is 2. First order with boron trifluoride, first order with ammonia. Now let's take who answers part C. Part C, it asks, what is the value of the rate constant for the reaction? Rate is equal to K times ammonia concentration times boron trifluoride concentration. So I'll substitute experimental values that have 0.25 on both of them, and that would be number 1. I'll just use number 1. So the rate is 0.2130. K is 0.2130 molarity per second over 0.250 molar squared, and what you get is 3.408 molarities to the minus 1 seconds to the minus 1. You're only allowed 3 sig figs. So 3.41 molarity to the minus 1 seconds to the minus 1 as your final answer for that question. D, what would it be if you increased the boron trifluoride concentration to 0. Or if you decreased it to 0.1 molar, and the ammonia concentration was increased to 0.5 molar. Now that you know your rate constant, you can say rate is equal to 3.41 molarities to the minus 1 seconds to the minus 1. Mind you, this would be the rate constant at this temperature, which was, I don't know if they mentioned what temperature it was carried out at. They didn't even mention temperature in this one, so you have to assume it was done at the same temperature, because if you change the temperature, you will change the rate constant. Rate is equal to K times the concentration of BF3 times the concentration of ammonia, which are as depicted over here. So 3.41 molarities to the minus 1 seconds to the minus 1 times 0.1 molar times 0.5 molar, and what you get is 0.1704 molarities per second. Only 3 sig figs allowed, so you're going to say 1.70 molarities per second. And for part D, we're done. And the parallel question would be 30 for that one. The last one I want to do with you is 31.
Consider the gas phase reaction between nitric oxide and bromine at 273 degrees Celsius. It shows you the reaction. I'll write it on the board in a minute. The following data for the initial rate of appearance of NOBR were obtained. Determine the rate law. It's a similar type of question. Let me copy the data for you.
It's time to change this marker. Point. Oh my gosh, this is not good. Marker is cracked at the back, so it dried out completely. Let's hope that's not happening to the other ones too. That's never happened before. That's a first. It's a first for me. So 0.1, 0.25. 1, 0.35, bromine is 0.2, 0.2, 0.5, and 0.5, and then the initial rates are 24, 150, 60, and 735 molarities per second. So first question is determine the rate law. So let's look at the data. If we look at trial 1 and 3, no, look at trial 1 and 2. In trial 1 and 2, the bromine concentration is kept at 0.2. So any change in rate will be attributable to the change in nitrogen monoxide. And the nitrogen monoxide concentration is becoming from 0.1 to 0.25, so it's 2.5 times as much. So if it's first order, it should give you 2.5 times faster rate. Instead, it gives you more than 5 times. In fact, as it turns out, you have a 2.5 times increase in concentration. If you square 2.5, you get 6.25. And if you multiply 24 by 6.25, you get a 150. So that would mean that it's second order with respect to nitrogen monoxide. Is there another way we could determine the same thing? Not really, because, yeah, I mean, we could use the experiment 3 and 4, but now you have a 3.5 increase. So 3.5 times fast, it should be 3.5 times faster, or the square of 3.5. So if you're looking at this data and it's second order, it should be the square of 3.5 times faster. 3.5 squared would give you 12.25 times faster. So this number times 12.25 should give you that number. Times 60 and you get 735. So we proved it 2 different ways, that it's second order with respect to NO. So the reaction is second order with respect to nitrogen monoxide concentration. Now, what is it with respect to bromine? If you look at trial 1 and 3, the nitrogen monoxide concentration is kept constant, so it's maintained at 0.1. The concentration of bromine is 2.5 times more. So if it's first order, 2.5 times 24 should give you 60. Let's find out. 2 times 24 gives you 48, plus another half, which is 12. 48 plus 12 gives you 60. That is first order with respect to bromine. So you can say the reaction is first order with respect to bromine concentration. Okay? So you use this one to find out order of bromine, and you can use either these 2 or these 2 to find out the order of the nitrogen monoxide. Now let's answer the questions that the book asks. So the rate law, rate is equal to some constant K, which we don't know yet, times the concentration of nitrogen monoxide squared, times the concentration of bromine. That's because I'm looking. Yeah, the other one had it as well. Okay, so it's bromine concentration. So that's the rate law. And for part B, I think we're going to have to erase because it's not going to be enough room.
31, it says, calculate the average value of the rate constant for the appearance of NOBR from the 4
Data sets. So what you have to do, yeah, we're definitely going to have to erase. But you guys have the text so you can follow along. So for part B, we're going to do it for all 4 data sets. We're going to enter all the data and find out the value of K for all 4 data sets. They should all be very close. So, given that rate is equal to the rate constant K times the concentration of the bromine times the concentration of nitrogen monoxide squared, we can say also that K is equal to the rate over concentration of bromine concentration times nitrogen monoxide concentration squared. So entering that into each time, you get a, so it's called the 4 data sets, K sub 1, sub 2, sub 3, sub 4, and so on. So you get the following results: 24 molarity per second over 0.2 times 0.1 squared, and the value of K that we obtained from that is 1.20 times 10 to the 4 molarities to the minus 2 seconds to the minus 1. For K sub 2, you have 150 molarities per second, but the concentration is 0.2 and 0.25 squared respectively, and it'll be 1.20 times 10 to the 4 that you get for that one. Molarities to minus 2 seconds minus 1. For K sub 3, it's 60 molarities per second times 0.50 times 0.10 squared, and that gives you, again, 1.20 times 10 to the 4 molarities to minus 2 seconds to minus 1. And K sub 4, I'm running out of room. I think I could do it. 735 molarities per second over 0.50 times 0.35 squared, and you still get 1.20 times 10 to the 4. So that's reassuring. If you had an experiment where you got results like that, and you average them all out, you still get 1.20 times 10 to the 4 molarities to minus 2 seconds minus 1. So it's reassuring when you have multiple data sets giving you the same result. So the average is, that's the answer for the part.
C or B? Let me see. Okay, the average, and then part C says, how is the rate of appearance of NOBR related to the rate of disappearance of BR2?
If the NO concentration is 0.075, I don't think I answered that part of the question.
Oh, it's how is the rate of appearance of NOBR related to the disappearance of BR2? They are occurring in a 1-to-2 ratio because the stoichiometry of the reaction is, I should write that down for you.
It's 2NO2 gas, no, not NO2, 2NO gas plus Br2 gas gives 2 NOBr. So these two are related 1 to 1. When you get 1 mole of NO disappearing, you get 1 mole of NOBr disappearing. If you get 2 moles of this disappearing, 2 moles of this are appearing, and this one is 1 to 2. So stoichiometry, what are they asking in the question? How is the rate of appearance of NOBr related to the disappearance of Br2? It occurs at twice the rate because of the stoichiometry is 1 to 2. The stoichiometry is 1 to 2. So for every 1 mole of Br2 that disappears. Part B. What is the rate of appearance of Br2 when NO is equal to 0.075 molar and Br2 equals 0.25 molar? Now that we know the value of K, we simply enter the values. So we're going to say rate is equal to K times Br2 concentration times NO concentration squared. If NO concentration is equal to 0.075 molar and Br2 concentration is equal to 0.25 molar,